And the next paper is examining the Hydra, simultaneously shared links in Tor and the effects on its performance. Wait, over to you. Thank you.
I will present our work today examining the Hydra simultaneous shared links in Tor and the effect on its performance. First off, to the introduction. So Alice is connected to the Tor network over a circuit to a website, and Bob does the same thing, gets a relays, builds a circuit also to a website, and if many users do that, circuits could overlap, so a shared link could occur. And the problem with shared links in Tor, they are between two relays, there's a TLS connection, and multiple circuits are multiplexed over this connection, and they share the same congestion window. And if a loss event occurs, then for one circuit, also the other circuits suffer. And that problem is called cross-circuit interference in Tor. And the underlying problem is head-of-line blocking, where we have three streams over one data line. You have packet loss. Not only stream 3 suffers, sondern also the other streams. And there's already solutions in Tor to solve the head-of-line blocking or the cross-circuit interference, but we were more interested, or there was a gap in knowledge, how many shared links there are in Tor. So our research question were how many simultaneous active shared links exist currently in the network and what influences this number. The second, how many simultaneous active shared links exist when the demand grows further, and how does the CCI influences the current network performance in the face of simultaneous shared links. First off, some definitions. So an active shared link is a link between two relays where at least two active circuits are multiplexed, and an active circuit is one which at least one cell was transferred in the last second. So our measurement resolution is 1 second for the simultaneous part. First off, to research question 1, how many shared links are in the network? On the x-axis, there's a Tor network scale, so 100% would be the complete Tor network, and 50% half of the network in terms of users and relays. And we measured at first with shadow at 1% scale, 10% scale, and 25% scale, how many active shared links exist, that are the purple dots, and also the active circuits. And these active circuits grow linearly with the Tor network scale, so we can also reach 100%. And to do that, we built our own simulator that we verified for correctness with not only with shadows, also with the Tor path selection algorithm. And we used these active circuits as input as well as the consensus documents. And then we can simulate how many shared links are there for different Tor network scales. And we have also different influences here. So, for example, internal and external means here all active circuits are internal circuits, and external circuits, internal circuits connect, for example, to onion services, and external circuits go out to the internet. And the link between relays can be directed or undirected. That means the network path forward can be different from the network path backward. So asymmetric routing in that sense. And we measured that there are, for the 100% scale network, for these 4 cases, there are between 4 and 6% of shared links. So we have a range where the real number can be. Then for the second research question, number of simultaneous active shared links when demand grows. There are, in that sense, basically 3 cases. So if the number of users grow, that is correlated with the number of active shared links, and the number of relays grows, and we have the same situation as before, where the number of simultaneous shared links would go down. If the number of relays grow, then that would be the same. The number of active shared links would also go down. And we focus on the last part, where the number of users grow faster than the number of relays. On the x-axis, we have the active circuits per second, and on the y-axis, in percent, the active shared links. The red part is the current network. These numbers are a bit different than beforehand because it is based on the year of the complete year of 2021, and beforehand it was only based on November of 2021. And we have here between 4 and 7% of shared links. And if the network would come to its bandwidth limit, which is marked in gray, with a gray box, then we would have around 9 to 15% of shared links. And for the last research question, the performance implications, we did shadow measurements for 2 scenarios, one for without packet loss and one with packet loss. And we use PCTS, so the problem goes away. And it's very similar to PCTCP, which is already published in the literature. And PCTCP uses 1 TCP connection per circuit and robs these connections in an IPsec tunnel. And we don't use an IPsec tunnel, we just use 1 DLS connection per circuit in that case. And that comes around, that solves the problem for the cross-circuit interference. And as you can see here, here's the transfer time for 50 kilobytes. And in the normal case, there's not much difference. For the first scenario, the blue and the orange line. But for the green and the red, where packet loss occurs, there's a significant difference in performance. And we also measured this for 1 megabyte and for 5 megabyte, and it's basically the same. But keep in mind that here we used a 25% network in shadow, simulated a 25% network in shadow, not 100%. So in the real network, this would be, the performance gain is not that huge. To conclude, the CCI problem is still relevant, or could be more relevant if the number of users grow and the relays stay nearly constant. And also, Tor has integrated some performance features, but they don't solve that problem. And since version 4.7, Tor has also end-to-end congestion control, but we don't know at the moment how that influences the CCI problem. That was it.
Okay, thank you. So first message up on Zulip. You're using 1 TLS per circuit. Are you multiplexing those TLS sessions over 1 TCP connection? If so, doesn't that still have the same head of line blocking problem?
No, we don't multiplex this over one TCP connection. We use, say, separately, so it doesn't affect it.
Okay, thank you. Any questions from the room? Or right. Nope. Right. Thanks.
Yeah, I'm just curious, like, what impact would like a TCP congestion control algorithm that just avoids generating packet loss, such as, you know, BBR or similar, would perform? Because in that case, the congestion window is kept so that packet loss generally wouldn't happen due to congestion. In that case, wouldn't this also avoid head-of-line blocking? Because you'll still have head-of-line blocking from the congestion window, but you wouldn't really have congestion-based packet loss on that link anymore, assuming that the network is good.
We didn't look into that problem. I don't know at the moment.
Yeah, since I think there might be some really interesting interactions between your work and the specific congestion control algorithm that you configure TCP to use. Yeah, that's what I was thinking about.
Thank you.
Any more questions here? Yeah, one over there. Yeah, we want to have the remote people be able to hear what you're saying, so yeah, please wait.
Are there any implications for attacks like denial of service? Could an attacker creatively construct paths in order to induce this CCI and accomplish some goals that way?
An attacker could construct or create many circuits in that ways that it leads to the problems. That, of course, yes.
Any other questions? No? Okay, let's thank you, speaker. Thanks, speaker.